Hello everybody, this is Dr. Eldik and today I will talk about chapter 4 in semiconductors, and it is about the bipolar junction transistor or BJT. In the bipolar junction transistor, we add either N-type or P-type to the diode. So we know the diode is PN. Here we have N more in this side, or we can add P to the other side. So we either have NPN or PNP. So this is mainly the transistor. So we have this is a bipolar transistor, could be PNP or NPN. We usually concentrate on the NPN because the concept is the same for both of them. There's no big difference between them. So as I said, we add a P-type or N-type to the PN junction, which make it NPN or PNP. This is a NPN. It consists of what? Consists of this N-type, we call it emitter, and the P-type, we call it base, and N-type, we call it collector. Every one is different from the other one. The emitter is heavily doped, so it has a lot of electrons. It's N-type, of course, so it has a lot of electrons. Okay, and the P-type or the base is P-type, but it has less. It is very thin. So this one here should be, of course, thinner, but just for demonstration here, we make it like this. But usually this base is very small with respect to the emitter. The collector is the N-type, and it is larger than both, larger than the emitter. Okay, so this one is very small. This one is much larger than the base, and the collector is much larger than both the emitter and the base. So when you look at it here, imagine that we have them like this, not connected to anything. So what happens that we have some electrons here and holes here. Then the electrons will move from at the border here. The electrons will move from here to here, from here to here, filling the holes. This will make a depletion region exactly like in the diode or the PN junction. Same on the other side. So here actually we have two depletion regions. So of course, to overcome this depletion region, you have to connect it to certain voltage. We can model the NPN bipolar junction transistor by having two diodes like this, because it's PN from this side and PN is the other side. So we can make it a diode here, base emitter, this is a diode, and base collector, another diode. Okay, but remember the property of N, the emitter, and the property of the collector. The collector is large, the largest one, and the emitter is small, but of course it is high with respect to the base, but it is heavily doped. It has a lot of electrons. Okay, the resistance between from B to E to E to the emitter, from base to emitter, and from base to collector is usually small because this is the forward direction. So from base to emitter and from base to collector is very small. The resistance opposite direction from the collector to base or from emitter to base, of course, is very high because in this case this is the reverse bias. But the resistance between the emitter and collector is usually high. Why? Because one of them will be reverse. One of them, because they are opposite to each other. If one of them is if you are talking about, for example, from emitter to collector, this one here is forward, this one is forward bias, and this one is reverse bias. This is supposed to be bias, not base. Sorry for that. Okay, so the resistance between emitter and collector is usually high. And there are different ways to bias the bipolar junction transistor. You can, for example, assume that we have a voltage here. This one VEE, call it VEE, to connect to the emitter, and the VCC is connected to the collector. If both of them are positive, Then in this case, the two diodes here will be, both of them, they are reverse bias. They don't have any current. So this one is useless, but this is one way. Okay, so this is the first way to connect DC voltage to them. Okay, but if we reverse them, if we have VEE and VCC are all both negative, like this one and this one, so in this case, both of them will be forward biased. Then you will have a current here and you have a current here. Okay, what if we have one is positive, one is negative, one is forward bias and one is reverse bias? So what will happen here? So this one here, you see, for this one here, this is a forward bias in this loop, but in this one here, no, it is reverse. So what is the situation here? What will happen? In this case, let us look at this figure. So if we look at the electrons, okay, this is a forward bias. This section here, or this loop, is a forward bias. Okay, so in this case, this is the electrons are moving in this direction. Then they will force these electrons to go to the base. So they will overcome this depletion region and continue in the base. But what happens at the base, because it is very thin, then these electrons can either pass this base and go to the collector. So the electrons are moving to the base to fill the holes, but because this is heavily doped and also the base is very thin, then the electrons will continue in the or to the collector. So they will create the current here. And this current is very small. This IB is very small. So actually you can say that this current is the same. It's almost the same. It's almost the same. Of course, if you notice that this current is emitter current is equal to IB and IC. But because IB is very small, then you can approximate it. You can say IE and IC are almost the same. Then the current, this current here, these electrons will move in this direction, okay, and it will continue like this. So this is what happened in the NPN junction if we connected forward here and the reverse bias here. Forward for the emitter and the reverse for the collector. This is what happened. And then we can see here the relations. As I said, IE equal IB plus IC. As I said, IC is much larger than IB. Then you can say that the emitter and collector currents are almost the same. Because this is a forward bias, B and E, then the voltage between B and E is almost 0.7 volt, because this is almost a diode in forward bias. Okay, but VCB is bigger number, bigger than 0.7, but it depends on the circuit, of course. Okay, remember that all what I'm talking about now is electron currents, so negative currents. So electrons are moving. But when we solve circuits, usually we use the conventional current, which is positive charges. So we have to change the arrows in the other direction. So this part here is electron currents. The current is moving in this direction. But in reality or in circuit, when we solve it, we assume that we have a positive current. So this is IE. So we have IB in this direction and IC in this direction. Then they will add together to give you IE according to Kirchhoff current law. So again, we have IB and IC. They will be added together to give you IE, which is the emitter current. This is the symbol of the NBN transistor. So we have a collector here, emitter, and base. So as I said, it is IC, IB. They will add together to give you IE. This, when we talk about these currents, these are the positive currents. They are all positive currents. So again, this is a schematic of the NPN. The PNP will be different, because it's opposite, because it is just instead of NPN will be PNP. The arrow here in both of them is always referring to the N, is going to the N type. So here's N, PN. So the arrow is going to the N. Here is PNP. So PN. So it is moving in this direction. So this is how we differentiate between the two symbols. If the arrow is going this direction, this is NPN. If it is going this direction to the base, then it is PNP. But usually, as I said, we usually use this one. Okay. So now, what is the relation between the currents? Usually, as I said, IC and IE are almost the same. IE is bigger, of course, but the relation is like this, because the ratio is alpha. Alpha equal IC divided by IE. So for sure, alpha is not more than 1, cannot be more than 1, because IE, this is the current that will be divided. Okay, IC and IB will add together to give you, here it is, IC and IP will add together to give you IE. So IE is bigger, of course. But IC and IE are almost the same. So alpha is very close to 1. Very close to 1, but less than 1. Less than 1. So let us say 0.99, 0.98. So the value for alpha is usually more than 0.95. Because as I said, IC and IE are very close to each other. Beta, this is what we call it here, the ratio of the, this is a ratio between the collector current IC divided by the base current, which is IB. IB is very small. So in this case, beta is a big number. Beta is IC divided by IB. Usually it is 100, 200. Okay, and of course, you can find the relation between alpha and beta because you know that IE equal IC plus IB. Okay. Beta is also called HFE. This is the hybrid parameters in any transistor. When you look at the data sheet for any transistor, you will find the H parameters. HFE, this is one of the hybrid parameters of the transistor, is beta, the same like beta. There's no difference. And this is also called the current gain, because it is the ratio between IC and IB. So IB is the input here, IC is the output, so it's almost high as a current gain. Okay. Okay, so now if you want to relate alpha and beta, alpha equal beta divided by beta plus 1, and beta is alpha over L1 minus alpha. You need to remember or know these relations here. Of course, since beta is a big number, as I said, so beta over beta plus 1 is a small number, small, less than 1 for sure. Beta over beta plus 1. Assume that beta is 100, for example. Then 100 over 101 is almost 1. 0.9, whatever, 0.99, something like this.